Everyone's heard of energy. But if someone asked you right now to explain what it really is, would you know how to answer clearly? Most people associate energy with electricity, movement, or the force needed to get out of bed in the morning. But in physics, energy is something much more subtle, and at the same time, much more powerful. Imagine having an incredible tool. It doesn't just describe, but also predicts the behavior of everything around us. From the fall of an apple to the fusion of stars. Energy does exactly that. It's not a substance you can grab with your hands. In fact, it's an essential property of any physical system. And what's most impressive? It can reveal what's going to happen even before it happens. In this video, we're going to deconstruct this concept that's so present, but often misunderstood. You'll discover why energy is considered one of the most important concepts in physics, or perhaps even in all of the exact sciences. How it transforms, how it's conserved, and how it can be compared to a secret currency that governs the universe. Ready to see the world through different eyes? But first, let's break a myth that almost everyone believes. When we hear about energy, it's common to imagine something that flows, like electricity coming out of an outlet, or fuel burning in an engine. But from the perspective of basic physics, this idea doesn't hold up. Energy isn't a type of matter or a magical entity. It's a property of physical systems, just like temperature or mass. It's always associated with something like an object, a field, an interaction. In isolation, it simply doesn't exist. Think of it like color. You never see blue floating loose in space, but you see a blue sky, a blue shirt, a blue wall. Color is a characteristic that only makes sense when applied to an object. The same goes for energy. It's not a resource that moves from one place to another. Actually, it's a way to express quantitatively how systems interact and transform. And you know what that means? It allows us to describe physical phenomena with incredible precision, like the movement of a ball or the operation of a turbine. What happens is that by treating energy as a property, physics opens the way for creating robust and exact physical models. Instead of imagining some invisible something traveling through bodies, we start working with measurable quantities. The potential energy that an object has when elevated, the kinetic energy it gains when falling. All of this is part of the same reasoning. This approach transforms energy into a powerful tool for understanding the world. But this goes beyond what you might imagine. Because energy, in physics, doesn't just serve to explain what has already happened. It's a tool for predicting what's still going to happen. That's right, it works like a scientific time machine. By understanding how energy is distributed and transformed, we can anticipate the behavior of a system. This applies to simple things like the time it takes for an apple to fall, and also to complex events like the collision of galaxies. So energy offers a solid foundation for well-founded predictions. Let's test this with a practical example. Imagine you want to know how long it takes for a stone to fall from the top of a building. Instead of measuring directly, you can use the potential energy it has at the initial height. This energy will transform into kinetic energy during the fall. The calculation allows you to estimate the speed and impact on the ground. Isn't it incredible how an abstract concept can predict the future? This shows how energy conservation becomes a powerful tool in practice. Curiously, energy is more present in your life than you imagine. Another example is in the daily use of your smartphone. The battery stores chemical energy that transforms into electrical energy to power the screen, processor, and sensors. The more apps you use simultaneously, the more energy will be consumed. Or think about when you charge your phone. You're transferring electrical energy from the outlet to recharge the chemical energy in the battery. Energy, in this context, works like a kind of universal currency. It allows us to measure and plan each action of the device. Get ready for an analogy that will change your view of energy. To make the idea of energy more intuitive, imagine a fictional city. In it, the economy revolves around a currency we'll call jails. Each citizen needs jails to do anything. Climbing in high heels requires some jails, increasing the speed of a car too. But here's the fascinating detail. In this city, there's no production or destruction of jails. The total always remains the same. It just changes form or place. Let's see how this works in practice. Someone can spend jails to climb onto a high platform. Later, they can come down and recover part of those jails in the form of movement. It's as if height were a type of energetic investment that can be converted into speed. The same goes for other systems. What changes isn't the total value, but how it's distributed. This dynamic directly reflects how energy transformation occurs in nature. This leads us to one of the deepest discoveries in physics. This analogy helps visualize one of the pillars of physics, the law of energy conservation. Even when everything seems to be changing like height, speed, or temperature, the total amount of energy in an isolated system remains constant. The imaginary city of Giales is an efficient metaphor for understanding how energy transits, never being created or destroyed, just converted from one form to another, like a fair exchange within the rules of the universe. But maybe you're wondering, how is this possible? One of the most fascinating aspects of energy is its ability to transform. Contrary to what many people imagine, energy doesn't have a fixed form. It can change from potential to kinetic, from thermal to electrical, from chemical to luminous. The most important thing is that even changing its face, the total amount is conserved. This is one of the great rules of physics, observed in practically all experiments we know. Let's see this happening in real time. Let's go back to the stone at the top of the building. When it's up there, it has gravitational potential energy. When released, this energy begins to convert into kinetic energy, which is linked to movement. The closer it gets to the ground, the faster it becomes. The energy changes form, but the total remains the same. It's like exchanging bills for coins. The value remains the same, even though the format changes. And this doesn't just happen in laboratories. This principle applies in everyday situations. The human body, for example, transforms chemical energy from food into movement and heat. A hydroelectric plant converts potential energy from dammed water into electricity. Physics doesn't worry so much about where it came from or where it went. It focuses on how this energy reorganizes. This shows us that energy is more than a measure. It's a key to understanding the interaction between physical systems. Now comes the part that will surprise you. The idea of conserving energy may seem simple, but it hides immense depth. When we say that energy is neither created nor destroyed, we're stating something that has never been disproven by any experiment. Think about it. Everything that happens in the universe, from a glass falling off a table to a stellar explosion, respects this energy conservation. It's a silent constant, always present, even when we can't see it directly. It's worth remembering that there's an important detail that few people know. For this conservation to be observed clearly, the system needs to be isolated. This means there can be no energy input or output. In the laboratory, we create such environments with maximum possible control. In nature, it's more difficult, but we can still calculate losses and keep the account balanced. The universe, no matter how chaotic it may seem, follows this rule with impressive precision. This means that physicists use an interesting trick. Physics uses this law as a kind of compass. If something seems to disappear, we know that energy hasn't been lost. It has just been transferred or transformed. This principle is essential for validating theories and predicting phenomena. If you understand this law, you already have a solid foundation for understanding much of basic physics. And the most curious thing is that this conservation is linked in a profound way to the structure of time. But that's a topic for the next point. Get ready for a connection that will blow your mind. Have you ever wondered why the laws of physics work today the same way they worked yesterday? Or why a stone will fall the same way, whether you're in the 21st century or 1,000 years ago? This happens because of a principle called temporal symmetry. It states that the laws governing the universe are constant in time. And surprisingly, this is exactly what guarantees energy conservation. Actually, there's a fascinating connection. The relationship between symmetry and conservation may seem abstract, but it's very concrete in physics. When a law of nature doesn't change with time, something is conserved. In the case of energy, its conservation is linked to the idea that time is uniform. This means that if you do the same experiment today and tomorrow, you'll get the same result. This allows physics to create valid models that work at any time. And who discovered this revolutionary connection? This concept was formalized by one of the most brilliant minds in science, Emmy Noether. Although her name doesn't appear as frequently as it should, her work showed that every symmetry in a physical system implies a conservation law. In the case of temporal symmetry, we have energy conservation. This is a fundamental and profound point in physics, and reinforces how much the universe is governed by surprisingly consistent patterns. Let me connect all the dots for you. Everything we've seen so far shows that energy isn't just a technical measure used by scientists. It's a precise way to describe reality. When we understand that energy is a property, not a substance, we begin to see the world more clearly. Falls, jumps, engines, atoms, everything works based on this invisible but reliable principle. Finally, we can conclude that energy conservation isn't just a rule to be memorized. It's a reflection of the deepest symmetry that exists, that the universe respects its own laws as time passes. This allows us to trust physics predictions and build models that work at any scale, from the trajectory of an airplane to the formation of stars. Energy connects us to the very structure of time and space. So, the next time you see something moving, you're witnessing the invisible dance of energy. Now that you know this foundation, it's worth asking, how does energy manifest in your daily life situations? When you run, heat food, or even when you think? Where is energy there? Physics is in everything, even when we don't notice it. If this content helped you understand this concept more clearly, subscribe to the channel and turn on notifications, because knowledge is just the beginning.